Hello. In the previous lecture, we were discussing something about principal argument. In this lecture, we are going to take study some properties of argument of a complex number. Some properties of the argument of complex number. So see what. We've already seen that argument is a multi-valued function. It represents geometrically the orientation of the complex number, and a principal argument is defined in order to make the argument a single valued function. So basically, whenever we make argument a single valued function, that particular single valued function is called as a principal argument of the number. Now, let us discuss a few properties. So property number one, remember that argument of Z, I'm not going to give you some proofs for this. The proofs for all these things are given in the textbooks. So I hope you are going to check them in the textbook itself. Although wherever necessary, I may give you some initiations or motivation as to how these properties may have been derived. So argument of Z is equals to minus of argument of Z conjugate. It's quite easy to see that Z is what? Z is simply, if Z is this, then what is Z bar? Z bar is simply taking the image of it. Okay. So if this is theta, this is certainly equals to minus of theta. So clearly from the figure itself, you can understand that argument of Z is equals to minus of argument of Z bar. However, please note that this property is not valid if Z is a negative. It is not valid. I'm writing it is not valid if Z is a negative real number. Why? Because you've already seen that if let's say Z is equal to minus of 4, or let's say in general, let me write if Z is equal to minus of A, where A is a positive real number, okay, then clearly you know that this would lie on the negative real axis. Okay, and if I write this, then whether I write Z bar or whether I write Z, they're one and the same thing, because if you are taking a conjugate of a real number, it remains the same. Both of them would remain equivalent to pi. So no longer this property is valid. So remember that this property is not valid, or this property cannot be applied, or this property, you can say, is not true if Z is a negative real number. Now let us move to second property. What can you say about this? Let us say that if Z1 and Z2 are two complex numbers, okay, then what can be said about the argument of Z1 into Z2? What can be said about argument of Z1 into Z2? See, for this, I will use the polar representation just to give you an idea. So if I'm saying that here we can see that I can write Z1 is equals to R1 e ki power iota theta 1. And similarly, I can write some Z2 is equal to R2 e ki power iota theta 2. I'm expressing them both Z1 and Z2 in the polar representation. Okay, this makes our task a little bit easy. And if I multiply them, let's say Z1 and Z2, what I will get, I will simply get R1 into R2. So this is the magnitude. We don't have to bother about it. And we'll get theta 1 plus theta 2, e ki power iota theta 1 plus theta 2. So if you really think, if one can clearly see that argument of Z1 plus Z2 is nothing but it is equal to theta 1 plus theta 2, which certainly is equal to what? It is equal to argument of Z1 plus argument of Z2. Okay, argument of Z1 plus Z2. More appropriately, in books you may find there is a expression written this way in order to this is more general expression, that is argument of z1 z2 is equal to argument of z1 z2 mod of 2 pi. One can verify this. It's quite easy to see. Just let us take one example. Let us say that z1 is equal to what? Let us say z1 is equal to 1, comma 1. And let's say z2 is equal to what? Z2 is equal to minus 1, comma. Okay. So z2 is minus 1, comma 1. And let's say z1 is 1, comma 1. So argument of z1 would be what? It will be equals to pi by 4. And what would be argument of z2? Argument of z2 will be simply 3 pi by 4. One can see that where one would lie, 1 comma 1 would lie here, and minus 1 comma 1 would lie here. So what you will get, you will simply get from here, it is equivalent to argument of z1 z2. Let us find argument of z1 z2. So z1 z2 it would be what? It is 1 plus iota into minus 1 plus iota. So 1, so this will be equals to what? One can clearly see that this is equals to minus 1 plus iota minus iota plus iota square. So this gets cancelled and you're going to get minus 2 comma 0. Okay, so minus 2 comma 0, it is a negative real number. The argument of minus 2 comma 0 or argument of z1 z2 would then be equals to what? It should be equals to pi, and which certainly is equals to argument of z1 plus argument of z2. However, if argument exceeds 2 pi, so argument of z1 z2 will be equals to what? Clearly one can see argument of z1 plus argument of z2. Now if your argument exceeds 2 pi, by which I mean, let us say I'm talking of something like this scenario. Let's say one number I have, let's say 1 comma 1 only. Let me place it this way. And let us say that another is somewhere here. Let's say somewhere here means what should I take? I'll take something that will exceed 2 pi so that you'll be able to get what I want to suggest. Okay, so let me take one example. Let us say z1 is equal to 1 comma 1. And or otherwise, let's say we'll take something like this so that you get a better idea. Just give me a minute. I think this I have to get rid of. Okay, sorry. So let us take one example here. Let us say another example. Let's say z1 I take let's say 0 comma 1. Let me take z1 as 0 comma 1, and let me take something like this somewhere here. So let us say this is your 1 comma minus 1. Okay, now what would be argument of z1? Argument of z1 is simply equals to pi by 2. And what would be argument of it? Let's say this is your z2. What would be argument of z2? So argument of z2 will be equals to what? If I take this way, so argument of z2 will be some 3 pi by 2 plus some pi by 4, or what you can say 2 pi minus pi by 4. I can write this as 2 pi minus pi by 4. So 2 pi minus pi by 4 is 7 pi by 4. Now if I add both of them, what I'll get? And let us also find argument of z1 into z2. So what is argument of z1 into z2? Z2 is 1 minus iota and z1 is simply iota. So z1 into z2 would be simply iota plus 1. See, clear? I hope it is clear. And what would be argument of Z1, Z2, Z1, Z2, 1 plus iota. So argument would be simply pi by 4. Now the point is this, if you add both of them, you're not going to get pi by 4. So it is not equals to argument of Z1 plus Z2. So therefore, what it would be equals to, just remember, just think about it. What it would be equals to, if I add pi by 2 to 7 pi by 4, what I will get? If I add pi by 2 to 7 pi by 4, what I'll get? I'll get 4 here, 2 pi plus 7 pi, which is certainly equals to what? It is equals to 11. Not 11, sorry. It is equals to, sorry, 9 pi by 4. 9 pi by 4. Okay, so this is equals to 9 pi by 4. So certainly here, this property doesn't hold true. What property holds true? Just take argument of Z1, Z2 equals to argument of Z1 plus argument of Z2, but don't forget to take the modulus 2 pi. Modulo 2 pi, sorry, modulus 2 pi, modulo 2 pi. So if you take modulo 2 pi, what you'll get? If you take modulo 2 pi, what would you get? If you want to convert into degrees or whatever, then you know that this is 2 pi. What is 9 pi by 4? 9 pi by 4 is equal to 2 pi plus pi by 4. So 9 pi by 4 modulo 2 pi, you'll simply get pi by 4, which is certainly equals to argument of Z1 to Z2. So more generally, you can write, whenever I'm not talking of principal argument, I'm talking simply of argument, then argument of Z1, Z2 is equal to argument of Z1 plus argument of Z2 times mod of, argument of Z1 plus argument of Z2 modulo 2 pi. This is the most general result. Okay, so these are two just. Similarly, one can also write this property, that is Z1 by Z2. If I want to find the argument of Z1 by Z2, then certainly it will be equals to what? It will be equals to argument of Z1 minus argument of Z2. And then you can take modulo 2 pi. And this certainly will solve your problem here also. And the derivation part is quite easy. You can write R1 e ki power iota theta 1, and here you can write Z2 is equals to R2 e ki power iota theta 2. And you know that Z1 by Z2 would be equals to R1 by R2 e ki power iota theta 1 minus theta 2. So argument of Z1 by Z2 would certainly be equals to what? Argument of Z1 by Z2 would certainly be equals to theta 1 minus theta 2, and which is equals to argument of Z1 minus argument of Z2. And in order to make certain adjustments that your angle doesn't exceed 2 pi, or for that, what I would do, I would simply write argument of Z1 by argument of Z1 by Z2 is equals to argument of Z1 minus argument of Z2 modulo 2 pi. So this is how you write these simple properties. Most of them, the proof is given in the book. So I'm not writing the proofs right now. I'm just giving you an example. I'm just giving you examples. Okay, I hope it is clear. Now, what about the principal argument? So let us take example. Let us choose Z1 equals to -1 and Z2 is equal to minus of iota. Let us choose Z1 equals to -1 and Z2 is equal to minus of iota. Then Z1, Z2 would simply be equals to what? Z1, Z2 would be simply equals to iota. And if I find the principal argument of Z1, Z2, it would certainly be equals to pi upon 2. Okay, it would be pi by 2. But argument of Z1, principal argument of Z1 would be equals to what? It will be equals to pi. If you remember, this is a negative real number. And argument of Z2, this will be equal to what? This is minus iota, this is minus pi by 2. Certainly, argument of Z1, Z2 is a principal argument Z1, Z2 is not equal to argument of Z1 plus argument of Z2. So you need to take care of all these things. Okay, you need to take care, because this will be equals to what? It will be equals to pi upon 2. Oh, sorry. Here it is quite easy. Here it is argument of Z1, Z2 is equal to argument of Z1 plus argument of Z2. Huh. Let me take another example. So this is fine. Here you can clearly see that there is no such discrepancy. The principal argument Z1, Z2, I think, excuse me for the mistake. I think this was fine. This was -1 and this is minus iota. So I think both when multiplied would give you an iota. Principal argument Z1, Z2 would be principal argument of iota, which is certainly equals to pi by 2. Argument Z1 simply of -1. So argument of -1 is pi. Argument of Z2, which is minus iota, is minus pi by 2. So overall, if you add both of them, you'll get pi by 2, pi by 2. So this is verified. However, if you just think about, let's say, let me take some another example. Let me keep it, let me write it this way. Let us take Z1 is equal to -1 only. That is fine. And not take Z2 is equal to iota only, not minus iota. Here, I think you will find a discrepancy. See, what would be argument of Z1? This is simply pi. And what is argument of Z2? This will be equals to iota. This will be equals to pi upon 2. Now there would be a problem. Argument of Z1 plus Z2. Sorry, argument of Z1 plus argument of Z2. Principal argument Z1, this I'm writing principal argument. This is equals to 3 pi by 2. However, what would be argument of Z1, Z2? You know that whenever we are talking of principal argument, we need to restrict our values from minus pi to plus pi only. Remember this. This is something that you already know. So principal argument of Z1, Z2, it is equals to principal argument minus of iota. And what is the principal argument of minus iota? It is equals to minus pi by 2. So what one needs to do, one needs to, if I want to, here if I want to do, I have to subtract it from minus 2 pi. So I have to subtract this result by minus. So basically here, if for this, if I want to write, then argument of Z1, Z2 would be equal to, as this, please mind it, this is principal argument, Z1 plus principal argument Z2 and minus of 2 pi. Why it is so necessary to subtract from minus 2 pi? In order to keep the principal argument in the range of minus pi to plus pi. This is why we do such things. Sorry. Okay. So this is something that you need to remember. Okay. Now, okay. So here you can note that one thing that you can note that even if we add the principal arguments, when principal arguments are added, then principal arguments are added, then it is not necessary, then it is not necessary that the sum remains the principal argument, that the sum turns out to be a principal argument. Okay, the above is the example. So in order to make it a principal argument, you need to do certain mathematics, and you need to, I don't know what to do, but the overall the attempt should be to put it in minus pi to plus pi. So this is how it is. Okay, and conversely, we've seen above. Conversely, by the above property, that is argument of Z1, Z2 is equal to argument of Z1 plus argument of Z2 modulo 2 pi. Conversely, if two non-principal arguments are added, non-principal arguments are added, it may result into a principal argument. It may result in the principal argument. So all these small statements you can keep in mind for your exam. If somebody asks you, I hope you are not going to get confused. Okay. So we have already written this thing, but I'm going to now in the background of whatever we have discussed. So we have already written that what would be the equality of complex numbers. So we have already written equality of complex numbers. So two numbers are said to be equal. Two complex numbers are said to be equal if and only if their modulus is equal and their argument is equal. But what if argument is like this kind of thing? Somebody is writing argument, because general argument if you are writing, then this particular thing can be 9 pi by 4 also. Okay, so this is 2 pi plus pi 4, 4 pi plus pi 4. So one has to remember that in order to write it more generally, it should be this way. Argument of z1 should be equals to what? Argument of z2 modulo 2 pi. Okay, in general, this would be more accurate way of writing the equality of complex numbers. So two complex numbers z1 and z2 are said to be equal if and only if modulus of z1 is equal to modulus of z2 and argument of z1 is equal to argument of z2 modulo 2 pi. So this is how you are going to achieve. We can refine the writing of equality of complex number. Now, what does it mean to multiply a particular complex number? Okay, so let's say, just giving you an example, or what do you mean by rotation? How can we understand that? See, suppose we have a complex number e ki power iota phi. Let's say we have a complex number e ki power iota phi. Here phi belongs to some real. And let us say another complex number, we simply have z. If I multiply z1 into z2, what I will get? I'll get z into e ki power iota phi. I hope it is clear. So how would you get this? How would you get this? So it is quite easy to see that if z is this, if z is this, then z into e ki power iota phi is nothing but it is equal to rotating this complex number by an angle phi. If I am writing this resultant, that is z1, z2, it is nothing but it is equivalent to rotating this z by an angle of phi. So basically this line, if I rotate by angle phi, this will give me the, this particular line is nothing but it is equal to z into e ki power iota phi. I can demonstrate a little bit of, not exactly, but a little bit of it by some example. Let us say the complex number z is 1 plus iota. And we clearly have an understanding to this, that this would be equal to this way. So what is 1 plus iota? It is equivalent to, argument will be equals to pi by 4. So this is 1 comma 1. Now, if I take another number z2, this is z1, let's take z2 equals to e ki power iota pi by 2. And if I multiply this, so z1, z2 will be equals to what? Z1, z2 will be equals to 1 plus iota. And what is e ki power iota pi by 2? It is simply iota. So it is equals to iota minus of 1. So basically it implies what? I am somewhere here. So it is 1 comma 1 only. Instead of 1 comma 1, you will get something like minus 1 comma 1. Okay, so this will be equivalent to this. This is minus 1 comma 1. I hope it is clear. So one can clearly see that minus 1 comma 1 is here. So this is some angle. So this angle clearly, if you do certain geometry, that you can find that this is equals to pi by 2. So if I rotate, if I want to see that this particular complex number minus 1 comma 1, how did I obtain? I obtained it by just rotating this vector by an angle of pi by 2. So if I'm multiplying this complex number z1, that is 1 plus iota, by e ki power iota pi by 2, it implies that this implies geometrically that I'm writing it implies the rotation of uh, 1 comma this particular complex number 1 by 1 comma 1 by pi by 2 radians. Okay, so this is how you do your things. Okay, I hope it is clear till now. Sometimes you need to really visualize the regions also. So let me just give you an example of one region. How would you visualize this region? How would you visualize this region? So clearly, if I would have said you, not this, if I would have said you that argument of z lies between 0 and pi by 2, how would you would have visualized it? So argument of z is equals to, it lies between 0 and pi by 2. It implies I'm talking of this particular region, right? Or had I written this way, had I written argument of z lies between pi by 6 and pi, how you would have written it? You clearly written this way that let's say this is your pi by 6 and then this is your pi. Okay, so argument of z lies between pi by 6 to pi means what? I'm talking of this region. Similarly, if I'm talking of argument of z minus 2 minus 3 iota lying between pi by 6 and pi, it implies what? I have shifted my origin and now I'm talking of the argument lying between pi by 6 and, let's say this is your pi by 6. Now I'm talking of this region. This, that is, argument lying between pi by 6 and pi means what? Now with the shifted kind of origin, I want to find the region. This would be that region there. The only difference is that had I written only argument of z lying between pi by 6 and pi, then this would have been the answer. But now I'm writing argument of z minus 2 minus 3 iota. It implies I've shifted my origin to 2 comma 3. And then this would be the, what you can say, this would be the shade, this shaded region would have been the accurate representation of this particular region. I hope it is clear. I hope it is clear now. Okay. So certain more things we are going to discuss. Let us just think about it a little bit. Questions I'm writing, not questions in general, but just think about these things, and then we'll discuss all these things. What do you think that this region would be? Set S represented by all those complex numbers z such that z minus pi by 2, argument of z minus pi by 2 modulus is less than pi by 2. So what does it represent? What does it represent? Just think about it. Okay. And similarly, try to find this also. Similarly, try to find a few more things I'm giving you. What does this represent? Suppose Z1 and Z2 belongs to C, and let's say both of them are non-zero. Then what is the geometrical interpretation of writing Z1 plus Z2 bar plus Z1 bar into Z2 equal to 0. What is the geometrical interpretation of this? Also, what is the geometrical interpretation? Let's say I'm writing, suppose Z1 and Z2 both belongs to complex, and Z1 is also non-zero and Z2 is also non-zero. And if I'm writing Z1, Z2 bar minus Z1 bar Z2 equal to 0, what does it represent? So these three questions I'm leaving you with. I hope in the next lecture we are going to start with this thing. A little bit of such more important things we are going to discuss. And then we are going to enter into one of the important aspects of complex analysis. That is, let us discuss, we'll try to discuss some topological aspects of the complex numbers, which shall be very important for your further discussions. I hope you might have got this particular lecture. Please try to revise all these concepts. These are important things. I found that students are, at times I found that students are not that well acquainted with complex number representation itself, and they find hard time to understand this subject. So I hope you're going to take these lectures quite seriously. Till then, take care.